Welcome to today's New England HIMSS webinar presented by premier sponsor Dimensional Insight, titled Decoding Healthcare Data with AI, Practical Tips for Unlocking Actionable Insights, presented by George Deely, Vice President of Healthcare Applications, and Joshua Levering, Business Intelligence Healthcare Consultant, both with Dimensional Insight. As Vice President of Healthcare Applications, George is responsible for Dimensional Insight's product direction in the healthcare market. His past experience working with healthcare organizations to streamline information delivery mechanisms gives George a unique perspective on the challenges all organizations face in effectively distributing business-critical information to varied user sets. Joining George today is Josh Leverling. At Dimensional Insight, Josh engineers actionable discoveries for healthcare organizations, leveraging his data science bachelor's from WPI. His efforts span standard application development and maintenance alongside the implementation and customization of active partner solutions. A reminder today that all lines have been muted upon entry. Please send your questions via the Q&A feature and we will answer them at the end of the session. Please join me in welcoming Josh and George today.
Thank you, Elisa, and thank everyone for joining us. We're very excited to share with you some of the things that we've learned as we've delved deeper into the world of artificial intelligence at Dimensional Insight. So recently, all the buzz has been about generative AI, aka Gen AI, and that's the world of ChatGPT, Google Bard, large language models, where AI is generating new information based on patterns in large amounts of data, like the entire internet, or a combination of that and more constrained domains like medical information, as is the case with Google's MedPalm 2. Now, there's no doubt about it. This is game-changing with useful applications in healthcare, such as the combination of ambient listing and clinical note generation for provider-patient interactions. And that holds the promise to reduce clinician burnout, improve the patient experience, and enhance care quality. But everyone's talking about Gen AI, right? So we're going to talk about something a little bit different. And we're going to refer to it as quantitative AI, quant AI for short. And that's the use of AI, machine learning algorithms, and large data sets to make the quantitative predictions. It's an area where there's also been significant progress, but also something that Gen AI isn't that good at really quite yet. Though it probably likely will be someday, and we'll be getting to that a little bit later. So there's a lot to know about quant AI that can start helping you today. So here's what we're going to cover and what you can take away. So first, a quick review of the basics of AI and machine learning for those of you who may be less familiar, and hopefully it'll also be a good refresher for those of you who are. And specifically, we're going to look at how and where this is being applied in healthcare, including both opportunities and risks. Next, we'll look at who's involved in imagining, creating, and using systems that employ these technology. And an intriguing aspect of this is the emergence of the citizen data scientists. And we'll talk about what that is and why it's important and how it may be relevant to you. Then we're going to take you through a case study of how quant AI can be applied to a specific scenario to generate useful and actionable insights in a healthcare setting. And we're going to be going deep into data science on that one. And finally, we're going to project how quant AI and Gen AI will likely converge to take advantage of what both of them are good at. Oh, and thank you for the questions that some of you sent in advance. We've tried to weave answers to some of those questions into the presentation, but feel free to add questions to the Q&A, and we'll get to those at the end. So let's start with some overall perspective on AI with a few quotes that underscore some important points. So Sam Altman, the on-again, off-again CEO of OpenAI, says that AI is not a replacement for human creativity, but rather a tool that can augment and enhance it. Well, let's hope that's the case, but it's probably a reasonable assumption. Over on the right-hand side, we heard this as a recurring theme at the New England HIMSS conference on AI back in the fall. And that's that, to paraphrase, AI in and of itself isn't a strategy. It's a set of capabilities that can be harnessed to help inform and realize and truly reimagine organizations' strategies, missions, and goals. And then finally, at the bottom, Dr. John Halamka, formerly of BI Deaconess and Harvard Medical School and now at the Mayo Clinic, who's among the foremost thinkers and doers in this area, has said that anything that we do in AI starts with high quality, curated data. And that's particularly the case in healthcare. So we've got some good foundational ideas to set the stage. So what is it that AI actually does anyway? And we'll use the terms AI, machine learning, and data science somewhat interchangeably here. So the machine learning algorithms at the heart of AI do essentially two things. They classify and predict. So some everyday examples of classification in social media, for example, whether it's LinkedIn or Facebook, they frequently, often annoyingly, suggest who you may want to connect with, right? And they do that by classifying people who are likely to have a connection with you based on similarities to other people who have a more direct connection to you. Now, for prediction, another social media example, recommendations on things that you might be interested in, whether it's movies, deals, or specific products, based on some estimated likelihood that you'll respond. And that likelihood concept also applies to things like weather predictions, medical diagnoses, and maybe the most relevant for many of us, traffic routing, as with Google Maps, Waze, et cetera, where we truly depend on those quantitative predictions. Now, these two things, prediction and classification, are subtly different, and they're commonly used in combination with one another to solve problems. And they can even use the same algorithms to achieve their goals. Now, machine learning algorithms can operate in two basic modes, supervised learning and unsupervised learning. The supervised approach, which is probably the more common of the two, uses example data called training data sets to discover patterns between input data and some outcome, the thing that you're trying to predict. Now, in healthcare, think about images, X-rays, MRIs, CT scans. They help with diagnosis, right? Now, aspects of those images, like the fracture in the example, can be identified or tagged. And with enough data, the association between the images and the descriptive information becomes clearer. And then those patterns from the training data sets can be applied to new data. Now, in the case of the image example, the new images could be classified as having fractures or not having fractures, or even grouped into different types of fractures. We can give these algorithms some hints called features that are derived from the data. For the radiology images, there might be some information in the narrative interpretations that could help. So things like findings and abnormalities. Identifying these things is called feature engineering. More on that a little bit later when we get into our case study. So unsupervised algorithms try to detect patterns in data without the benefit of those hints or features, or even clearly defined outcomes. And they do that by clustering together things with similar characteristics. So think back to the imaging example without the hints. So just go find some images that are similar to one another and put them into groups. Now, that seems a bit counterintuitive, but with enough data, patterns begin to emerge, especially around anomalies. Think of another example, fraud detection in medical claims. Certain patterns just stand out as unusual over time. So then there are the many algorithms that do the heavy lifting of machine learning. And here's one way to organize and talk about them. And if nothing else, this will expose you to some of the terms that you probably heard thrown around and what they refer to. So starting in the upper left-hand corner and working clockwise, traditional statistics like linear and logistic regression. And most of what goes on in machine learning algorithms has its roots in regression. Then there's time series, detecting patterns in data over time. And you could do these with some effort without a large-scale machine learning computing environment. You could use a spreadsheet, but with pretty limited data. And of course, with a machine learning approach, these algorithms are that much more powerful. So the next group, computer-assisted statistics. This also uses techniques that have been around for a while, in some cases centuries, like Bayesian inference, but they're really not practical without large-scale computing. And they do progressively better with more and more data. We'll talk about decision trees in our case studies a little bit later. Then classification algorithms like k-means and k-nearest neighbor. They emerged to process the massive amounts of data that became available with a combination of large-scale computing and data generated by the internet. And you find these at the heart of systems that do things like data discovery, image recognition, and intrusion detection. And then finally, there are the neural networks behind deep learning algorithms. The names and abbreviations here are a real alphabet soup, as you can see. But these are designed to actually mimic the way that the human brain works by using layers of regression that add meaning to data as it passes through them, identifying patterns as they go. And with enough example data, they're able to figure things out just the same way that we humans do, but with the ability to think really fast, access massive amounts of knowledge, and remember just about everything. So imagine if we could do that. So now let's talk about how this applies in healthcare. So there's no doubt about it. AI has great potential to help advance the now quintuple aim goals of healthcare. But some of the applications come with significant risks to patient well-being. So this slide is a variation on one that Dr. Rebecca Macheras, the Chief Medical Information Officer at Mass General Brigham, used during her excellent presentation at the New England HIMSS AI conference. And she described how Mass General Brigham uses a formal governance structure to evaluate projects that involve AI. And in the chart at the right, as you move from left to right on that scale, the types of projects involve greater risk to care quality and patient safety. And on the right side of that vertical red line, you really need to start thinking of your AI system or any other IT systems really the same way you do about medical devices, therapies, and medications. They need to be extensively validated against real clinical data. But on the left side of the line, there are some opportunities to apply AI where there's still potentially significant benefits to improving efficiency and productivity, but with fewer risks around safety and quality. And that's particularly true for administrative processes. So here's some examples of those administrative use cases organized into the categories that we talked about earlier. So forecasting, things like patient waiting time, anticipating staffing requirements based on projected workflows, and getting out ahead of process bottlenecks when workflows get overwhelmed and begin to break down. Then there's predicting, things like future health and utilization risk in populations to target intervention opportunities, identifying which patients and customers are likely to be going elsewhere for their care, attrition, and then estimating when the cash from payments is coming in. That's as critical as ever in healthcare. And then classifying healthcare claims that are most likely to be denied, detecting fraudulent activity, and then assisting with hiring, development, retention, and other human resource related activities, and lots more, of course. So now let's talk about how all of this gets done in practice. So AI is definitely a team sport. It takes a diverse collection of knowledge, experiences, skill sets, and perspectives to figure out what to build, how to build it, and then how to integrate it into how work gets done. So here are some of the roles in a typical team involved in imagining and building AI systems. So at the center are the subject matter experts. They're the ones who have some of the best insights as to where the opportunities are. The stakeholders need to make sure that the initiatives are supporting things that are important to the organization. Information consumers are the folks on the front lines who are going to use and ideally benefit from what's being produced to achieve those stakeholder goals. Data analysts help to translate what's in the data into meaningful insights. Data engineers build and maintain the pipelines of data necessary for the AI systems to work. And then finally, data scientists are the specialists who understand how to combine data and algorithms to tease out the magic that's possible with AI. But one of the biggest challenges is communicating amongst all of these roles, right? As you can see from the things that we've talked about so far, this can be a real Tower of Babel. But there's an interesting trend that may help with that necessary translation, and that's the emerging role of the citizen data scientist. And that's someone who has the right balance of these skill sets to understand the big picture. And what's central here is the subject matter expertise, whether it's nursing, pharmacy, imaging, medicine. These are all really deep domains that take years of experience just to scratch the surface. And these folks are likely already information consumers. They may be stakeholders. So adding some of the technical skills like data analysis and a basic understanding of things like data engineering and data science put them in a great position to help imagine, guide, and maybe most importantly, successfully deploy AI projects and systems. So what is it that you ask that the citizen data scientist actually does? Well, first of all, there probably isn't a job or job description called citizen data scientist. It's more the way that you might work within your role. And here are some of the things that you might do. Understand the potential of AI and focus it on the highest value opportunities. Contribute your subject matter expertise to pretty much every aspect of the project. Identify risks that only someone with deep subject matter expertise might see the potential for connecting the information produced by the AI system with potential actions and responses. And then with some basic skills, data, and imagination, test out ideas with informal rapid prototypes, AKA skunk works, right? Shh, don't tell anybody that we're working on this. And then prompt engineering. What even is that anyway? It's figuring out how to ask these AI systems the right questions to get useful information, which in and of itself takes domain expertise and imagination. So that's enough background information. Now let's dive deep into our case study. And we're going to get into some fairly hardcore data science here, but don't get intimidated. We'll tie things back into how you would use what gets produced as we go. So I'm going to turn it over to Josh Lovering, our resident data scientist.
Thank you, George. So for the next 20 minutes, we'll take a look at a case study that we did to apply quantitative AI to a data set of our own. And the topic that we chose was forecasting wait times for an emergency department. Karl Popper, known for his contributions to the philosophy of science in the 1900s, said, "Non-reproducible single occurrences are of no significance to science." And this is representative of his concept of falsifiability as a criteria for a good scientific theory, in that it is only reliable when proven correct if it had the capacity to be proven wrong. And this puts an emphasis on not only exploring new ideas, but also validating and reproducing already known solutions. We had read this paper from the medical analytics group at Mass General Brigham, where they discussed a few projects, and one in particular was wait time forecasting for some clinics. They found their successes in weak learning applied by gradient boosting machine learning models, and ultimately their most successful approach leveraged deep learning. And we'll delve into what those mean a little bit later on, as the authors' transparency and industry-wide motivation encouraged us, and we're excited to pursue a similar approach using our own ED data. So let's say we could forecast these wait times. Where's the value? One of the biggest impacts we see would be on staffing, especially in regard to anticipating and reacting to overcrowding. Also, depending on the methods used, we may be able to interpret the significance of certain factors and how they impact workflow. So this could reveal limiting factors and bottlenecks. And ultimately, we aim to prevent reductions in the quality of care. It's been observed, and this may sound obvious, that overcrowding in emergency departments can result in quality of care reductions, possibly due to delays or less time spent on individual patients. And lastly, the forecasts could be presented to patients directly, say in the waiting room on a monitor, where they may make their own decisions. So in this phase, it's important to note that we might introduce subject matter experts and stakeholders to get their perspective on the potential value of a product with their realistic understanding of how it might actually be leveraged. Are there individuals in their organization that would be able to act on this information? Before we get into our approach, here are a few relevant concepts worth introducing. A data pipeline is a series of processes used to transform our raw data into our end result, and it can be visualized to represent the flow of the project as a whole. Feature engineering and data transformations are processes in which we create relevant variables from our raw data that can be interpreted by the machine learning models. Cross-validation is when we split it's more of a generic term for resampling training data so we can more accurately estimate the quality of our models. So let's say we average the results from 10 different tests instead of using just one test to estimate the quality of the machine learning model. And lastly, modeling involves training a machine to capture patterns and relationships among our variables that we may either be able to see or not. Okay, so we started off with a pre-existing process. We already have some ED data that we use for the development and demonstration of one of our applications, and it's already been processed. So specifically, we used two data sets for this project. We had the ED log, which is an encounter level data set with timestamps and other visit details, and the ED census, which is an hourly census containing all the patients in the ED at any given hour. So our first step was to break this down to a 15-minute census, which better represents how we would implement this in the real world, where we would want up-to-date wait time estimates. So we would be running predictions at least every 15 minutes, and we could go more granular than that. And then we engineered our features and performed our experiments and tried various approaches before ultimately evaluating our final model and deploying the results from there. So our goal is to make predictions for near future wait times based on the current census. So specifically, the wait time that we're forecasting is the time from a patient's arrival to when they're seen by a doctor. And our features consist of information that we could pull from the census. Most notably, we have turnaround times, acuity, which is the severity of a patient's injuries. We have date time features to introduce the seasonality and time-based components. And we had a bunch of lag features that describe recent past periods, such as a turnaround time from an hour ago or a day ago or a week ago. And then these features are transformed as needed, whether they're categorical, cyclical, quantitative, or otherwise, to convert them into a machine readable format. And because of the model's dependency on the current census, we end up training 672 different models, each one capable of predicting one of the 15-minute intervals from now until a week from now, of which there's 672 of those intervals. And that's because of the dependency that we introduce with the current census. As we don't know what the census will be a week from now, we have to train a model to predict a week ahead based on the current census, and so we need separate models. And here to fully leverage our data and anticipate what might be worthwhile features, we can get the perspective of subject matter experts at this point who may have an intuitive feel for the factors, in this case, most relevant to workflow and wait times. And the citizen data scientist might come into play in the process of transforming this data into that machine readable format. So weak learning is the process of combining multiple not so strong models, weak learners, together to achieve a better performance than any individual weak learner would achieve alone. And this can be represented by the idea of teamwork, where a team comes together stronger than the sum of its parts. One way to do this uses gradient boosting, where the weak learners are trained sequentially, one after another, each one focused on resolving the mistakes made by the one prior. And in this case, those weak learners are decision trees, which is a machine learning algorithm that works by repeatedly partitioning data based on feature values. And each tree will focus on different aspects of the data, and then they all come together to form what's called an ensemble. And this approach is convenient. It's useful because it's convenient, as we can throw everything at it. The decision trees do their own feature significance. They determine which features to use whenever they partition the data. And that transparency makes the results interpretable as well. And this method works when there aren't any individually amazing features that can carry the predictions entirely on their own. And it's also great at capturing complex patterns in the data. We tried other approaches too. That includes, but isn't limited to, the some traditional time series forecasting using ARIMA, for example, which you may have heard of, and others as well. But the focus was on the gradient boosting. And we found our successes landed with the light gradient boosting machine, which is an open source framework that's available in a variety of programming languages. And it not only performed the best for us, but it was also one of the quicker and more efficient ones, which is well suited for having 672 of them working together. So here on the left, we can see some of our testing scores. The mean absolute error is the average error for a given prediction in minutes. So say we forecast a 30-minute wait time and the mean absolute error is 10 minutes, then that would mean the true value was generally within 30 plus or minus 10 minutes, which for real world wait time data isn't too bad. We grouped and ranked some of the individual models based on their R-squared, which tells us how well the data fit to the model. And so we can see that within the first 6 hours, the results are quite reliable. Within a day, they're still strong. And then beyond that, it becomes much weaker, but there is still some predictability throughout the rest of the week. And on the side, we have a couple charts to display predictions over a day and then over the rest of that same week. And here we can start to see some of that slippage over the course of the full week. And we've included an 80% confidence interval. That is to say, we're 80% sure that the true value lies within this range. And that can be useful in making decisions based off these predictions, as we'll see in a moment. So from here, we'll briefly transition over to some corresponding dashboards. There are 3 pages that make up the dashboards. There's the patient-facing page, a staff-facing page, and a final page with some of the details and metrics regarding the model. So we open up to the patient-facing page, intended to be displayed within the lobby of an emergency room or the waiting room there on a monitor. So we want to keep the details specific to what's relevant for a patient and also for ease of viewing, as they may be reading it from afar. So we could opt for not having the chart and just focus on those current wait time predictions. However, it can be useful, and a picture speaks 1,000 words. So today, let's say, we can see there's a bit of a wait time right now. So for example, if I had brought someone into the ED here, and maybe I left my car in 20-minute parking, I might take this chance to move it after we check in. The staff-facing dashboard is intended for more detailed viewing. The same information is repeated here as is on the patient dashboard, and we can also see a full week forecast as well as a surge threshold to help alert staff of possible overcrowding. And the threshold is determined from anomaly detection ran on the past 5 weeks. We also have a breakdown of the current census by status and acuity level to keep informed on the current distribution of patients. As a staff member, you might monitor the surge predicted for early this week, and as it gets closer, if the forecasts are still high, we may adjust staffing accordingly. In this case, it's more of a minor surge, nothing totally out of the ordinary. But if we, for example, saw the lower bound of the confidence interval past that threshold, that would be extreme, and we might be more likely to take action. The model dashboard displays specific details about the current model and its performance. So each time the model is retrained, all the data from the last few years would be used, and then we would leave out the 6 most recent months. And those recent months are then used for testing and evaluation to accurately assess the model before a final model would be retrained on all of the data to be used in deployment. So here are a couple of those recent testing windows. And overall, they're very representative of what we've seen. There were some other cases that performed better and some worse. The first 24 hours is reliable, as we see in both charts, and then after that, the consistency can fluctuate. So real-world wait time data will vary from day to day, and we see that it can be hard to pinpoint. As we see in some of these examples, the spikes aren't fully captured when multiple days in the future. So it's important when interpreting these to remember that the predictions would be reran every 15 minutes. And as they come closer and closer to the current time, they would be more reliable. So in our staffing example, once we see these actionable forecasts within the 24-hour or 12-hour, or especially that 6-hour range, we could more confidently take action. And that still leaves enough time for necessary staffing adjustments. Over here, we also see the top 10 most significant features identified by the model. And in our case, these aren't particularly actionable, so there's only so much we can do with that information. However, if more actionable features were used, their significance could be leveraged to improve workflow. For example, I recently read a paper where an emergency department in the UK was experimenting with workflow improvements, and they tried having a doctor in charge of triage, which allowed for see and treat, which is when a patient, for example, just needs some stitches, and so they take care of them immediately during triage and send them on their way, instead of putting them back in the queue. So if we had a binary feature to indicate which census blocks had a doctor in triage or not, we could learn more about the impact. And in this paper, they also experimented with other methods of restructuring workflow and reducing the number of steps a patient takes in the course of an ED visit. So ultimately, there's more potential for a takeaway from the feature significance. However, we need to expand upon our feature list to really leverage that idea. But ultimately, to refine these dashboards, we'll work to get feedback from subject matter experts and stakeholders, and ultimately end users, to determine if the use cases that this presents are valuable and what information and format actual end users might benefit from the most. So what did we learn from this project? First, the gradient boosting approach was a success for us. And also due to the transparency of decision trees, we can see how often each feature was used and how each feature improved the performance. So this indicated to us that the turnaround times and the date time features were the most significant, and that the lag features were particularly useful, especially as we make predictions further and further throughout the week. And ultimately, we have a vision for how this could be used to improve workflow, most notably making staffing decisions ahead of time and reacting quickly to these overcrowding situations. So we were successfully able to reproduce the value of this approach for ourselves on these clinic-based wait times. Now, where do we go from here? There are more options that we would like to explore. For the weak learning regression approach, there's more exploration to be done within our feature engineering. There's plenty of things we could do, and here's a few examples. We could implement rolling averages, which would be similar to our lag features in introducing the recent past. We could experiment with changing around our transformations. We could take an approach where we provide each of the different 672 models with a unique feature subset tuned to perform best for that time frame of prediction, instead of using all of the features for all of the models. And lastly, introducing live features could have huge implications, that being weather, events, and pulling activity from nearby facilities, which I believe is something that emergency departments already leverage. And for the time series forecasting approaches, there are plenty of exploration to be done in that world too. There's seasonal and non-seasonal approaches. We could do more experimentation with the traditional univariate models where we forecast just our single response variable over time. And there are also some time series models that can handle multiple variables, where we might introduce some of our features, mostly the date time features, so as to not introduce a dependency on the current census, but still allow us to introduce those like day of week and hour of day differences. And lastly, there are some deep learning approaches known to work well on time-based data. And we didn't want to start with these, as the simplest viable approach is often going to be best. However, there's some evidence that would suggest that these may work really well. To tie this up, I'd like to take a step further back and look at the bigger picture. The emergency department is just one part of a larger healthcare organization. And so far, we've considered the implications that these predictions may have within the ED itself. However, when possible, this data could be permeated even further. So, for example, if there's an influx of patients in the ED, that would plausibly lead to more hospital admissions. And this could result in more occupied beds, and then departments such as surgery and radiology may need to cancel scheduled appointments in favor of emergency care. So anticipating this ahead of time could help the healthcare organization as a whole react more quickly. And that's something we'd like to keep in mind for how to make the most of this data. With that, I'll pass it back over to George.
Thank you, Josh. Okay. So for our final section, we've used our imaginations to project how quant AI and gen AI may converge in the future. So we can start by looking at what each of them brings to the party. So quantitative AI, done well at least, has well-curated, precisely defined information. It has high levels of integrity. There's structure where it's necessary. It has well-defined query languages to access data. It's a good source for training data based on the access patterns of a specific user community. But it does require some adult supervision. Now, Gen AI, for its part, has incredible large language model capabilities that produce human-like content that can in turn be combined with data from specific domains. It has convenient human interfaces like speech recognition and natural language processing. And it seems to have a pretty good idea as to how to present data in meaningful context reasonably well, better than you'd expect. And it learns dynamically. The more examples, the better it gets. But it's subject to what's come to be known as hallucination, literally making things up. So to test things out, we created a little experiment. Now, we know there's some DI customers in the audience. What we're presenting today is strictly experimental. These are prototypes to help us work through the possibilities, as you heard from Josh. So don't get too excited quite yet. So we configured a chat bot to help new users begin to use an analytics system quickly, with the goal of reducing the number of steps necessary to get to useful information. And then we use this to envision how quantitative AI from an analytics system could be integrated into the Gen AI user experience. Now, we've used our own technology and applications for the example, as Josh did, but the concepts apply pretty generically. So first, a little bit of background information. So Dimensional Insight creates analytical applications to support decision-making in healthcare. And one of those applications is called the Emergency Department Advisor. And it's built around a family of KPIs or measures focused on ED operations and workflow. And each of those measures is curated and defined with metadata that's embedded in the system. The actual data is extensively validated in client projects. Now, that information can be used for analysis to present information in a variety of useful formats like this dashboard. Now, that's very powerful, but admittedly, there's a learning curve. It takes some time, experience, and practice to figure out what's available and how to put it to work. So thus the analytics assistant chatbot. So we started by loading that metadata that I just described, basically the names of the measures, the categories that they belong to, and their narrative descriptions into Anthropic's Claude AI assistant. Now, Anthropic is a company that was founded by two of the lead researchers who left OpenAI. This is actually a very simple process. First, you extract the metadata from the system. This is what it actually looks like within the application. You put it into a CSV file and upload it via a chatbot dialog. And the first thing that Claude does is to come back with some feedback that it understood roughly what you were trying to do without any additional input. So you can see that it begins to feed back the measures that were brought in. And it does that without any other input. So it's got a pretty good idea of what we're trying to do. So next, enter our new user. So they're a stakeholder, subject matter expert, who's recently joined the organization, and they've been tasked with figuring out what's going on in the emergency department. It's a burning platform with long wait times, diversions, boarding, and more. So the first thing that she will likely want to know is, what data do I have to work with? And she might just start asking the chatbot questions like, please give me a simple list of KPIs for understanding ED throughput. The please is actually optional. And Claude does a reasonably good job of coming back with a relevant list of those measures, given the input that we gave it, which is a combination of measures themselves and some description around it. And then interestingly, it adds its own commentary in the paragraph below based on what it already knows in its large language model about ED operations. So next, our hero decides to focus on ED boarding and asks for some more information on measures related to boarding. And back comes a pretty complete list of boarding measures with our definitions and some additional insight into what ED boarding is and how that data could be used to optimize ED operations workflow. We found that pretty fascinating and weren't even expecting it. Now, eventually, we're going to need to get specific here, right? As in, give me some actual data to work with. So we might want to ask about the long-term trends in excess patient boarding time. Now, remember, we haven't given Quad any actual data to work with, just the metadata. And it seems to be able to figure out both where we're going with the question and that it really can't answer it because it doesn't have the information that it needs. But it does actually make a pretty noble attempt at a general response. So you see down here in this paragraph at the bottom, and the bullet points in the middle, these are things that it actually knows about ED boarding and some interesting insights across the country. Now, instead of that, what we actually want is real, trusted quantitative data from the system that represents the source of truth. And this is where we start to diverge from what the chatbot actually does, at least at this point. We've just pasted some screenshots of data associated with the measure, but it's not a big stretch to imagine how this integration could work. It's pretty much a data plumbing challenge. We know the measure already. The query provided a time frame, the metadata that the system already has. It can get us to where in the system that data is available. And importantly, it can also provide a reference to the actual source of the information, including an opportunity to further analyze it. So this link down at the bottom is a hot link, and that could conceivably take us to an area where we could interactively analyze the information. So there was a spike in the data. We look at the chief complaint of the ED visits. We might want to go deeper into that and look at the post-discharge diagnosis information and further analyze that to understand what might be driving those excess boarding times. So it kind of got us to the right place where we could do the analysis that we wanted to do. And you can kind of understand how this could work. The chatbot's API could make a call to the analytics systems API to query and retrieve this type of information. That's actually not that's not a huge stretch. But admittedly, that request was around retrospective data. Old news, you say, right? But our ED problem solver probably wants some insight into what's going on right now, as well as projections into the future. And that's where we could tie in a query to the predictive models that Josh described. And that could look like this. So this is a great example of quant AI and gen AI working together. So all good stuff, right? But admittedly, nothing you couldn't get from the system itself if you knew where to look. So what's the potential for this over the horizon? You can imagine a few possibilities. Training data sets actually created from the access patterns from the user community's queries. So dynamically generated query code to answer increasingly complex questions with that reliable data from the quantitative system. And one of the things that Gen AI, such as Google Bard and ChatGPT, are good at is actually dynamically producing code. If you want a Python routine that can traverse a binary tree, you ask for it, you actually get the code, and it runs. And then continuous adaptive learning with more and more data and new capabilities. So the more data, better it gets. Capabilities like helping to interpret that overwhelming amount of data that's available in the analytics system to make some sense of it. And that's the key. Lots and lots of data, finding patterns in the data. So I'll leave you with one closing thought along those lines. This is a quote from the Time magazine article on Sam Altman as the CEO of the year. And bear with me because I'm going to read this, but I thought it was fascinating. Hopefully you will too. So OpenAI researchers began to train the first models in the GPT series. And with each iteration, the models improved dramatically. GPT-1 trained on the text of some 7,000 books. It could just about string sentences together. GPT-2, trained on 8 million web pages, could just about answer questions. GPT-3, trained on hundreds of billions of words from the internet, books, Wikipedia, could just about write poetry. And that's not to say anything about GPT-4 and some of the other things that are coming down the line. So, wow, just imagine the possibilities in another few years. And it will likely involve the quantitative AI, generative AI convergence that we've been discussing. So hopefully you found that informative, useful, even inspiring. So in a few minutes, we're going to open the floor for Q&A. So please start submitting questions if you haven't already into the Q&A feature. So in the meantime, a few words about today's webinar sponsor, Dimensional Insight, from Lindsay Goldfarb, Dimensional Insight's Director of Healthcare Marketing.
Thank you, George. As George mentioned, I'm Lindsay Goldfarb from Dimensional Insight. We are an 8-time best-in-class learning analytics provider and a proud longtime New England HIMSS sponsor, as well as the sponsor of today's webinar. So as you've heard today, you all know healthcare is constantly evolving and innovating, and what lays the foundation for much of this transformation is data. So here at Dimensional Insight, we empower healthcare with personalized analytics, helping you to turn that data complexity into clarity for smarter decisions and real results. So if you want to learn more about maximizing your clinical, financial, or operational outcomes with some of this AI-powered analytics, you can scan this QR code that's up on the screen now and chat further with us. So I do see plenty of questions coming in to the Q&A. So now I'll turn the floor back to you, George and Josh, to answer some of those questions. Thank you all.
And thank you, Lindsay. And Elisa will be providing the handout of the slides here. So if you don't get the QR code, you can get it with the slides. All right, well, let's move over to questions now. And we'll start with a few of the questions that came in ahead of time. And one of those was, what are some of the technologies and platforms that we see as beneficial, and which ones have we used? I mentioned chat, Anthropic's Claude. We use that extensively internally at Dimensional Insight to build our internal knowledge bases. We've used OpenAI, particularly the APIs, to build the types of prototypes that we're talking about here. But I'd like Josh to talk a little bit about the technology that he used to build these predictive models.
Sure, yeah. The work behind what we saw today was using some open source libraries from Python, and specifically scikit-learn is one of the more popular ones that we leveraged for the machine learning side of things. And yeah, and Python as a whole is open source, and so are a vast majority of the libraries there. I think that's a great resource. They also have some newer libraries that are more approachable for coming to an end solution with less code. And they take away a little bit of flexibility, but they add a lot of convenience. And so I think they're great for exploring data sets as well. And then, yeah, ultimately, I think those are some of the bigger tools. A lot of the times here, the getting to an end result requires some manual implementation. And so getting straight to some source code using Python or R, which are both, I think, some of the two more popular ones, both just as good for these sorts of problems, is a great way to go.
Yeah, we talked a little bit about the citizen data scientists. One of the fascinating things about how you access this data science technology is the fact that it typically doesn't require a lot of code. In some cases, it's just a few lines in R and Python. So, for someone who doesn't have a data science degree, it's actually becoming more and more practical to try these algorithms and approaches out.
Yeah, and if you are researching a very specific idea or project you want to pursue, there's plenty of articles you'll find online with entire implementations that have the code and the public data that was used for them. So that's a great starting point. You can just get your hands on that and then tweak it from there.
We had a very specific technical question, Josh, that you can probably shed some light on. How do you impute nulls? What factors should be considered when you're imputing nulls? Because you probably dealt with that a certain amount with the ED data.
Yeah, it's yeah, that's definitely an important thing to consider. Some models can't handle them at all, and others can. But either way, a null could skew the results. So oftentimes you would handle that with imputing a reasonable value, such as the mean for that column, or maybe just a rolling average. In time-based data, you might want a rolling average, which would be the mean for a few of the closest records. Or if it's applicable, you could replace them with another value. And often in doing that, another option is to include a separate feature that corresponds to that feature. And if you impute one of the records, then the second feature would be a binary indicator, and you could indicate whether that value was imputed or not. And that can help some models handle those better, or not take them into as much consideration. There was
So here's
oh yeah, go ahead.
No, go ahead, Josh, finish up.
Sure, yeah, well, so there's another question that came in earlier about, it asked about the importance of real-world data in augmenting clinical trials, especially in the areas of cancer research. And, especially with image recognition, which is a lot of what you might be referring to with cancer research, lots of data is super helpful. And there's opportunities to sort of fabricate training data based on existing data using bootstrapping or other techniques, but nothing beats the real thing. And not only with real world data can we get more and more, but we can introduce a variety of data so that we don't end up training a model that's been fit maybe on a specific sample that might not be representative of a whole population. So I think those are some of my initial thoughts reading that question about the importance of real world data.
Yeah, I think another trend is as population-wide data sets become available, there are better opportunities to simulate what historically we've thought of as clinical trials, which are somewhat biased because they're samples. Whereas if you have entire population data sets, as some countries do, like New Zealand, then you've got a better opportunity to do multiple simulations, multiple trials of various disease sets. So as we've talked about here, more and more data is that much more powerful.
I want to clarify, there was another question too, asking about the difference between forecasting and predicting. And it's a great question because I use them, they're somewhat interchangeably due to the context of our data being time-based. And I think of a forecast as specifically a time-based approach where the model will learn on a series of sorted values, and then it can be used to predict X number of intervals in the future. And so classically, that doesn't allow for other features. You just have your one response variable projected over time, whereas a regression or a prediction, there's no inherent order to that data. And we're using it on time-based data, but you could also not. So we can introduce features and a corresponding value, and the model will learn with this labeled training data how to come up with a likely response value for a new set of these features. And then to do this with time-based data, we can introduce features that represent the time, such as categorical representations. Is this record in a certain month? Is it in January? Is it a Sunday or a Monday? And then what hour of day is it? And those can be represented categorically or cyclically to introduce the cycle of the 24-hour period, for example. And so in a regression, the data doesn't need to be sorted. And in a forecast, we're just very specifically working with time-based data. And so here we did a regression on time-based data, which is sort of in the middle.
So in lieu of time, do you want to answer one more question since it's right up at the hour?
Let's see if we could find one that we could answer really quickly. Let's see, how do students get into this sector, particularly in UK? Are there internship opportunities, mentorship programs? Yeah, there actually are some great mentorship opportunities within HIMSS. To give a plug for HIMSS, local HIMSS chapters, similarly for ACHE, American College of Healthcare Executives, great opportunities for mentorship there. Some companies like ourselves, Dimensional Insight, sponsor co-ops and internships, which is an opportunity to get firsthand experiences as well. Lisa, is that it, or do we have time for one?
So I will provide a report to you with all of the questions that you didn't get answered today. And to answer Brian's question, I will be sending a post email that will include the recording for today's session, a copy of the handout, and also the CP HIMSS credit for the session. So I will get these questions to George and Josh, and they will provide answers back to me, and I will go ahead and include that information as well to everyone if they can get those back to me. So I do want to thank everyone for joining us. The hour flew by. Thank you to Dimensional Insights for being a continued premier sponsor of ours, and thanks to George and Josh. And if you wouldn't mind, as you exit today, giving us your feedback on the Zoom survey, we would very much appreciate it. So thank you again, George and Josh, and have a good afternoon and a good week.
Thank you.